you very much for that generous introduction. Yeah, I mean, there are a lot of nice things about all those other locations you mentioned, but they don't have green chili, so. Okay, so this is joint work with Alexander Mercier, who was an undergraduate research intern at the Santa Fe Institute at the time, a virtual one. This was during the dark days. And he was from Florida, and he's now at the Harvard School of Public Health as a grad student. And my good friend Sam Scarpino, who is a former postdoc at the Santa Fe Institute, who's very interested in epidemiology and also in the use of AI in health. And so this is one of those talks where he did like 98% of the work. So there's some joke where, you know, the senior professor says, when I say I mean we, and when I say we, I mean they. So as Melanie mentioned, and she is the other co-founder, this is this very fun interdisciplinary group of people around UNM and SFI and some other places as well, interested in all these issues around AI and ethics and fairness, or justice if you like. But that's not what this talk is about. I just wanted to put it up there because some of your own faculty are involved in addition to Melanie. And I want to point out, though, that in addition to computer scientists, there are like law people, psychologists, people who study misinformation, political scientists, which I think is the kind of interdisciplinary group you need to really study AI and its impact on society. And this is the sort of thing that we go to meetings of the New Mexico State Legislature and try to convince them that using opaque algorithms to make decisions about people that, for instance, have impacts on their constitutional rights is probably a bad idea. And if you work in AI, let me just mention that I don't think the usual notions of explainability or interpretability are enough for some of these societally important decisions. I think we need really a higher level of transparency. So we can talk about that maybe if you like. Anyway, here's what I'm going to tell you about. What is sparsification? Sparsification is the general act of taking a dense graph, probably a weighted graph, with lots and lots of links, and picking out a small fraction of its links that, in a way that somehow preserves something important about the structure of that graph. And in the particular version that I'm going to be talking about today, we're going to be keeping all of the vertices, which is a choice, right? You can also imagine summarizing a graph by clumping groups of vertices together into one large vertex. But in this case, we're going to keep all the vertices, but we're going to keep some fraction of the edges. And, you know, so we wanted to preserve something, but what should it preserve, right? So this is one of these problems which is application dependent. You know, what is it about the graph that you want this sparser graph to approximately keep? So there's been a lot of work both in graph theory and discrete mathematics and computer science around this, and also network theory. You might want the sparse thing to maintain important topological or structural properties of the graph, like important backbones, or if there are different communities, you might want it to preserve those. You might want it to preserve different dynamic properties, though, as well. So if this is going to be a graph on which something is going to walk around randomly, then you might want the flow of probability of where that thing is to work in a similar way. But I'm going to be looking at epidemics. So specifically, I want an epidemic model to act nearly the same on this graph as on the original graph. Now, why would we do this? Well, one reason is that at least if you code it up naively, and to be fair, there are fancier data structures that make this problem less bad. But if you are building an epidemic simulation on some big network, some social network or something, And and I'll explain in a moment what that means, but like,
I'm getting
each
full.
node here is a person or maybe a
Just make
city,
it work.
and it's either infected or susceptible or something, and then the infection is spreading to its neighbors. If you code it up in the most obvious possible way, then the running time to run the simulation is proportional to the number of edges. So, like, if on average the degree of this graph, the number of neighbors each node has, is like 100, that's 100 different ways that the disease could spread from there. And so the original motivation was that on some large networks that friends of ours and collaborators of ours were actually interested in simulating, it was taking a long time, and like a day. And the thing is that if you're doing epidemiology, you might want to do many runs of an epidemic simulation. First of all, because, as I'll explain in a moment, it's a stochastic process that is randomness. So, I might recover before infecting Jared, or I might infect Jared, and it's just allergy. So you might want to do many simulations and then look at the probability distribution you get of different outcomes. You might want to explore many different interventions, like, which nodes should you vaccinate, or which edges should you prevent people from traveling along, whatever. So anyway, there's this practical goal of a sparser graph will be faster to simulate. But there's maybe a better, more scientific goal, which is that if we do a good job of preserving the behavior of an epidemic model in this much sparser graph, that suggests that we've somehow done a good job of picking up the links in the original graph that are most important to the dynamics of the epidemic. For instance, the links that are most likely to transmit the disease and to create, a big outbreak in some other part of the network and so on. Okay, so I think that ultimately is a better motivation. Which links are the most important to disease spread? And you should maybe be thinking about, if you like to think about blackouts and power networks, for instance, in the power grid, then in a similar way, are there kind of simplified cartoons of the power grid where you would still do a fairly good job of predicting how a blackout might spread and so on. Although, incidentally, it turns out that blackouts and power grids generally don't travel along power lines the way epidemics travel along contacts between people, but that's another discussion. All right, so how might you choose which edges are most important? Well, suppose this is a weighted network. So suppose the weight of the edge is like how much time per week Jared and I spend with each other. Or if the nodes are cities, it could be how many people per week commute back and forth between these two cities. So one thing you might think is, well, gee, we should keep the high weight edges and maybe throw away the low weight edges. That's a thing you can do. And it turns out that, according to my friends, and maybe you can correct me, a lot of work on networks in bioinformatics, this is what we do, right? So, for instance, how do we observe how do we get a picture of the network of genes regulating each other? Well, one thing we do is we measure correlations between the activities of different genes in a bunch of mice. And we know, though, that some things will be correlated in our data just by chance. So we want to get rid of things that are just noise. So one thing people do is just choose a threshold. And if the correlation is above that, they say these two genes are really interacting. And if it's below that, we say they're not. So this is, well, I want to argue that this is not a good idea, at least in this application. So for a couple reasons. One is that this edge here might not be the only way to get from me to Jared. Jared and I might have lots of friends in common, and the total probability that the disease gets from me to him along one of those many low-weight paths might actually exceed the probability that it travels along this single high-weight path. So somehow we want to think about alternative paths. And also, what if there is a low-weight edge that stretches from New York to LA? Right, so not very many people fly back from New York to LA every week, but that could clearly play a major role in spreading the disease around the country. You know, the zombie apocalypse starts in New York and then spreads to LA. So if a low-weight edge is somehow structurally important, like if it crosses a long distance, we might not want to ignore it. So I don't think it's okay to just throw away low-weight edges and keep high-weight ones. Now in graph theory, we have various topological notions of the importance of an edge, the centrality of an edge or a node. One of them is called betweenness. So betweenness says, well, see this edge here, it's a low-weight edge, maybe this is New York and this is LA, but it's pretty much the only way to get from this clump in the network to that clump in the network, so it's important. And there are multiple definitions of betweenness. One of them asks, if I chose two nodes randomly in the graph, what's the probability that the shortest path between them would pass through here? And here it would be about a half, because if one vertex is here, the other vertex is there, well, then any path, including the shortest path, has to go through there. Betweenness, that notion of betweenness is not, I think it's not quite what we want. For one thing, it's a bit expensive to calculate, like n cubed time on a graph with n vertices. And we're interested in graphs with 1 million vertices. So it's a bit expensive to calculate, but also it has a kind of discrete math flavor where we're only thinking about the shortest path. And that's not what we want in this application. You know, we care about all the ways that the disease could get from me to germ. So somehow we want something softer or blurrier, which looks at all different paths. All right. So we want some combination of weights between this. What do we want? Okay. So I'm going to tell you in a slide or two what we use. But before we get there, I'm going to give you a sort of general family of ways to sparsify graphs. Okay? This is a general family in which our method will be one of these. So here's the general family. Give every edge an importance. You tell me what importance is. I mean, we just talked about different notions of importance. It could be the weight, it could be the betweenness, it could be something else. But whatever it is, you decide. And then we'll associate each edge with a probability proportional to that importance. And then we're going to do the following really naive thing. To get my new sparser graph, I'm just going to choose edges of the original graph without probability distribution, until I've chosen roughly the number of edges that I want to have. Okay. Now, we can talk about this, but if you've never seen sort of randomized algorithms, this thing of just choosing things randomly, it's very naive. But a lot of really good algorithms in computer science work this way, and often they have very beautiful analyses and proofs that they do work. So it might look kind of simple. It is random, right? There's no guarantee it's going to choose the edge that you think is most important, but you know, we're going to choose a fairly large number, but much less than the original number. But there's an interesting twist, which is that if I choose an edge E, in my new graph, I'm going to give it a larger weight than it had in the original graph. And that's because well, you can think of it in several ways. One is that it's sort of acting as a representative for all the edges that I'm not choosing. But specifically, I'm going to take the original weight and divide it by the probability you choose it when you choose an edge times the total number of edges you're going to choose. But this denominator is also the expected or average number of times that you would choose it. And if we choose the same edge twice, we just add up the weight each time we choose it. So the result is that with this reweighting, this funky E means expectation or average, the average value of the new weight is the same as the original weight. Okay? So that seems like it might be a good thing. In particular, if you make the adjacency matrix where the entries are the edge weights, or if you make this thing called the Laplacian, which is useful for a lot of applications, where you take the diagonal matrix of the degrees of the vertices, the total weight of the edges on each vertex, and subtract the adjacency matrix from that. This is important in thinking about how heat or probability or things like that flow around on graphs. Then on average, these things will be the same in the new sparse graph as they are in the old graph. On the other hand, it's a little funny to say that it's going to be the same on average, but we want most of these to be 0, because we want most of the edges to not be there in the new graph. So, and yet in some vague sense, we want the new graph to be close to the old graph, even though most of the edges are the same. So what do we want? And for this, we need a little bit of linear algebra, and I'm going to go through this quickly, but if anybody wants to do more, I can explain it. So let me now say what version of importance we use, okay, in that reweighting algorithm, and what that version of importance does for us rigorously, and then I'll tell you what it does for us experimentally. So there is a quantity which many, many different people have discovered or rediscovered, and some people call it effective resistance. So here's the idea. I take my original network, my weighted network, and I think of it as an electrical circuit. And on each edge, I put a resistance there, a resistor, whose resistance is 1 over the weight of the edge. So a high weight edge would be high conductance, which means low resistance. And then, then I define this thing called the effective resistance of an edge. So what I do is I take my ohm meter, and, you all have ohm meters at home, right? Okay. Anyway, so, and I put the two terminals on that U and V, and I measure how hard is it, what is the effective resistance of getting electrical current from U to V? And the thing is that counts not just the edge UV, but also all of the other paths by which current could flow from U to V. And, if you remember your EE courses, resistors add in series, but their reciprocals, or their conductances, add in parallel. So if there are lots of alternate paths to get from U to V, that will lower this effective resistance. Okay? And we'll say it's easier to get from U to V than you would have thought of if you were looking just at that one edge. And so these are like the alternate ways for me to get Jared sick. So now we define this measure of importance, which is this effective resistance times the weight. Why do we do that? Well, let's look at this quantity a little bit. So first of all, suppose that there really are no alternate paths, or that all the alternate paths are really long or involve really low weight edges. Well, then the resistance between U and V will pretty much just be that one resistor, and the resistance is defined as 1 over the weight. We multiply that by the weight, and we get 1. Okay. So notice, for instance, that if an edge is what graphers call a bridge, it's literally the only way to get from one part of the graph to another, this definition of importance is 1. And that's true whether it's a high weight edge or a low weight edge. Okay? It's just 1. So that sounds maybe reasonable. It's just important to include that edge in any sparse version of the graph. On the other hand, it will be significantly less than 1. It will be considered less important, less necessary to include if there are many alternate paths, many of which are not too long and involve weights that are fairly high. Okay? So, because if there are a lot of other ways to get from U to V, maybe it's okay if you don't include that edge. I feel like I may be beating a dead horse here, but that's the idea. Yes, Steve.
Is there an assumption here that the weights are always greater than 1? Or greater than equal to 1?
No, just that they're positive.
Because if they are less than 1, then 1 over WE can be greater than 1.
That's true. The resistance could be greater than 1. So, if a weight is like 0.01, the resistance would be 100. But then the product would still be 1. Yeah. So in particular, if you scaled all of the weights in the graph up or down by a constant, this quantity would stay the same. Okay, so
Chris, when you say long now, you mean long in terms of conductance?
well,
Which I guess is weights.
no, but you make a good point, right? So I mean, the length of a path is sort of the total resistance of that path, which is, the sum of the resistances. So yes, if it's topologically long, it involves many hops. It will probably be large if it involves, even if it's topologically short, but it has some really low weight edges, which are really high resistance. It will also be a high resistance. So yeah, some combination of the weight and the topology. All right. So let me tell you a few things that are so beautiful about this quantity. And these things, again, they've been rediscovered many times. If you've ever taken like a probability course where it looks at random walks, then there's this lovely fact that if you're wandering around on a graph, then the average time it will take you to reach some destination the first time is basically proportional to this effective resistance. That's cool. Here's another fact. I can't resist telling you the following. So you know that if imagine that you're on like the integer line and you're at the origin, and then every step to the next integer is a 1 ohm resistor. Well, of course, the resistance all the way to infinity will be infinite. Right? Obvious, right? It is also true that if you do a random walk on the integer line, you will return to your original starting point an infinite number of times. These turn out to be the same fact. If you are on a 2-dimensional grid, so at every step you move north, south, east, or west with equal probability, well, there are now many paths to infinity, and although each one of them has an infinite resistance, there are so many of them that, well, the resistance between you and the kind of shell very far away is still infinite, but only just barely. It sort of, diverges like the sum of the logarithm or something. And it's true that if you do a random walk in 2 dimensions, you will return to the origin an infinite number of times, but also just barely. Finally, in 3 or more dimensions, where you can move along all the edges of, say, a cubic lattice, there are now so many different ways to escape to infinity that the overall resistance is only finite. Which sounds crazy. And that corresponds to the fact that a random walk in 3 or more dimensions has a good chance of drifting off to infinity without ever revisiting its starting point. Okay, so there's some mathematical beauty to what I do there. Another nice fact, which turns out to be the same fact, these are all the same fact, is that you can compute the resistances using the graph Laplacian, and I won't go into this in too much detail, but it's this thing, the diagonal matrix of degrees minus the adjacency matrix. And you invert it, except it's not invertible. You use this thing called the pseudo-inverse, whatever, and then you can easily compute all at once all of the effective resistances from everywhere to everywhere else. You might say, but Chris, earlier you complained that between this took n cubed time to compute. And does it take n cubed time to invert a matrix or n to something less if you use fancy algorithms? It's like, well, yes, that's true, but clever people who I'm about to mention by name, who are not us, figured out that you can use a kind of random low-rank approximation to this thing and get good approximations in nearly linear time. Okay, so we can calculate these resistances approximately very fast. Anyway, like I said, this has been invented many, many times. Some people call it the spanning tree between these because one more beautiful fact. So, a spanning tree is this subset of the edges of a graph that reaches out and touches everybody and doesn't have any loops. So what if you chose, you have a big graph that has many, many different spanning trees. Suppose you choose one randomly, and suppose you choose it with probability proportional to the product of all of the weights of its edges. Okay? then the probability that a given edge will be included in that random spanning tree is exactly this. Again, if this is the only way to get from this part of the graph to that part of the graph, then any spanning tree crosses it, so that probability has to be 1. But if there are many other ways to get from here to there, the probability will be less than 1. Anyway, come on. You're all potential theorists. This is much more interesting than epidemics. All right. So these very smart people, Dan Spillin and Nikhil Srivastava, following on some earlier work by Spillin and Feng, proved a theorem showing that if you use this effective resistance, so I mean, they did this, we didn't do this. If you use effective resistance as your definition of importance, and if you choose a reasonably large number of edges, like some constant times n log n in a graph with n vertices, that may seem like a lot, but for a complete graph it'd be n squared. So as a function of as a fraction of a really dense graph, it's not very many. So if you do that, then with high probability, the Laplacian of the new graph is close to the Laplacian of the original graph in the following technical sense. And if you don't like this kind of thing, I forgive you. But what it means is that if I take any vector and put it on each side of this new Laplacian, what I get is very close to, it's within 1 minus epsilon and 1 plus epsilon of what I would have gotten in the original graph. So this is a spectral property, and what it means basically is that the new graph preserves, roughly speaking, both the eigenvalues and the eigenvectors of the Laplacian of the original graph. And what that means in particular is that if you had a linear dynamical system, like imagine that you have an amount of stuff or heat or something, and then it's spreading from each thing to its neighbors, right? The way that an initial blob of heat over here would sort of slowly spread out across the graph, that's something which is controlled by the Laplacian. And so what this says is that on the sparse graph, that would act very much the same as it does on the original graph. Okay. Now, being infected is not the same as being hot. And the way that infections spread is not quite the same as the way that heat diffuses to its neighbors. So this is why we wanted to do an experiment. And I see a hand up there, let me just say this sentence. So, epidemic models are nonlinear stochastic things. They're not linear flows of like either probability. So this theorem doesn't guarantee that the behavior of an epidemic will be similar on the two graphs. But it's strongly suggestive, and we wanted to do an experiment. Yes?
In your inequalities, there excellence related to probability or an error?
So if you want a smaller epsilon, you just take a bigger constant c. So it's like a lot of concentration inequalities. You take more random samples and then you get closer to the expectation. Does that answer your question?
Yeah.
Yeah. All right, good. I was going to say something here about choosing n log n random edges on a complete graph. That would give you a random graph, a so-called Erdős-Renyi random graph. And again, if you choose n log n of them, then, well, anyway, yeah. Anyway, that's the point at which a random graph becomes connected and at least touches every vertex in the original graph. Okay, good. So, well, now let's look at this thing called the SIR model. How many of you already know what the SIR model is? Let me tell you about the SIR model. It stands for susceptible, infected, recovered, although sometimes susceptible, infected, removed. So the SIR model is a model of epidemics where if you get the disease once, then you can never get it again, either because you're immune or because you're dead. Now, we know not lots of diseases are not like this, but it is kind of the first interesting epidemic model people do. So initially, everybody is susceptible, they have not yet gotten the disease, and a few people initially, like the zombies in New York, are infected. And then, at each little time step, if you are infected and you have a neighbor who's susceptible, then with some probability your neighbor becomes infected. And in addition, if you're currently infected, then with some probability you recover. Okay, that's the whole thing. And then by varying the rates of infection versus recovery, we can, if people recover fast enough compared to how much they infect their neighbors, then the disease is limited to little outbreaks. If the reverse is true, it will spread across much of the population. Okay. Technically, we're doing a thing called a continuous time Markov chain, where we imagine time being a real valued variable. It's not just an integer, and then in each little slice of time, there's some small probability of these infection or recovery events. Okay, so, why might resistance be a good idea? Well, if Jared and I spend time together, both in faculty meetings and in meetings with the dean and in meetings with our shared postdocs, if we have any, then presumably the total chances that we'll infect each other would be like the sum of all those. And well, yeah, it's like saying that if you have a bunch of parallel edges between two people, the weights of those edges would just add, and then the resistance would just go down, because it's one over the weight. Or also, suppose there are two communities, and there's a bundle of edges that cross between one community and the other. It seems like the total chances of the infection crossing should be proportional to the total weight. So in both, again, conductance adds in parallel, resistance adds in serial. So far the metaphor looks pretty good. Suppose that there's instead a long chain of infections to get from me to Jared. Am I picking on you too much, Jared? So the average time it would take the infection to get from here to here, because the infection travels at this rate, which is proportional to the weight, the average time it takes to get here would be, from here to there would be proportional to the sum of 1 over the weights, which is the sum of the resistances. So that sounds good too, because resistances are supposed to add in series. There's a little problem here about the distribution of the times at which it gets there, but the average looks right. Anyway, all right. So some other people before us had some similar intuitions. They didn't do quite the same experiments we did. So anyway, here are experiments, and this will basically complete the talk. So Alexander Mercier, my undergrad intern from Florida, he'd been studying white nose disease in bats. Do you know about this? It's this very sad disease that has been killing a lot of bats in North America. European bats were all immune, but North American bats were not. It's a fungus they get on their noses. It's very sad. So he had a huge network of that ecologists had collected of bat migration from one place to another. And this is one of the networks that was really dense and took a really long time to do the simulation. For this purpose, he gathered some census data, and this graph on the left, which is a solid block of purple, is a weighted graph where each vertex is a census tract in the United States. That's something smaller than a town or a city. It's how we do congressional districting, counting people. And then the weighted edge is the average number of people per day or per week, I can't remember, who commute between those two census tracts. And it's a very dense graph. It has 73,000 nodes and 26 million edges. And so the average number of neighbors each tract has is more than 700. So people go in all sorts of different directions. Now, I'm not saying that a census tract is a thing which is either susceptible, infected, or removed. We could have done a fancy model where each census tract or each town has a fraction of people which is infected or not, and then you would assume kind of strong mixing within that area, and then you would use the network between areas. We didn't do that. So, and in fact, there's some controversy in the epidemiology world about how useful these commuting patterns are in predicting disease. So I'm going to say something a little more modest. I'm not saying we can predict epidemics with this data. I'm just saying this is a real-world network with a ton of interesting structure. So you can see it more easily in the sparse version. You see concentrations of population on the coasts and around Texas and around Chicago. You see lots of local edges and then a few long-range edges. So it has communities. It has a mix of short-range and long-range edges. It's a fun, complicated graph. And we want to just try out our method on something like that. So what I'll show you is how well this works when you only keep about 7% or even less, like 5% of the edges of the original graph. Again, using this sampling method based on the effective resistance, reweighting the edges that you keep, and so on. So the resulting thing still has a lot of edges, but it's a lot less than the original. We tried two different initial conditions. One is we infect, again, JFK Airport. I got to hang out at the TWA hotel there recently. Anyway, cool. They took one of their own airplanes and made it into a bar. And then the other initial condition we tried is that 1% of people everywhere are infected. So we tried a localized and a dispersed initial condition. And then we compared this effective resistance with some other methods. So we compared it with that really naive thing I was dissing at the beginning of the talk, weight thresholding, just keeping edges that are above a certain weight. But we also compared it to some cousin methods where you do the sampling and reweighting. But for instance, one is where you give every edge the same probability, uniform sampling, we could try that. Another is where you give every edge a probability just proportional to its weight. Well, you could try that. And let's see how well it works. Okay. So now, the typical thing to show you would be like, over time, the fraction of people who get infected, and then the infection rises, and then as people recover, it goes back down. But that's so easy to get, I'm not even going to show it to you. I want to show you more, because I don't just care about what happens on average. I want a sense of the probability distribution of how the epidemic develops. In particular, for each node, I want to know the probability that your hometown, that the epidemic will arrive in your hometown from JFK. And so some nodes are going to have a high probability, some a low probability, and we want those probabilities to be preserved in the new graph. Okay, I want to get those probabilities right. So this is a plot where each dot is one of the vertices in the graph, one of the census tracts. The x-axis is the fraction out of many runs on the original graph in which it gets infected. And the y-axis is the average out of many runs on the sparse graph. So if everything was perfect, it would be right on the diagonal, and it looks pretty good. So in other words, it recovers the fact that some vertices are less likely to be infected, others are more likely. All of the sampling methods actually do fairly well. This is uniform sampling, this is sampling proportional to weight. Ours does, a little better. Just thresholding the weights is pretty terrible. Maybe there's some clever version of thresholding the weights where you also readjust the weights afterwards, but it looks as if it doesn't preserve what we want to preserve. It's a little bit more interesting to do this with JFK, the localized initial condition, because then the probability that your vertex gets infected is some combination of the distance from you to JFK, distance in whatever sense in the graph, and so on. And so here there's a nicer spread, and again, it seems to do a pretty good job. Weight-based thresholding does almost as well. Uniform thresholding, and then, sampling, not thresholding. Uniform sampling does pretty well, and again, simple weight thresholding doesn't. Well, I want to know even more. If your hometown is going to get infected, I want to know the probability distribution of when it gets infected. Again, not just averages. People average things too much. I want to see the distribution. So here we looked at 4 representative nodes, and conditioning on the event that they do get infected, we asked when do they get infected, and does that distribution look the same on the sparse graph as on the original graph? And actually, all three of the sampling methods, effective resistance, uniform, and weight, do pretty well. And this is interesting because, for some nodes, it's a pretty broad distribution of when they get infected, if they do. And for others, it's more sharp, and it seems to recover all that. Here is a total measure of error we looked at. So this is like, there's this thing called the Wasserstein or earth mover distance, which is kind of like how much you have to shift things in this distribution to turn it into that distribution. So it's a general measure of the distance between two probability distributions. So we measured that, and so the red here is effective resistance-based sampling, and even when you have just this, I guess this is 3% of the edges, this total error is quite small, and the other sampling methods do almost as well. All right, I'm almost done with all these charts. One of the reasons why these sampling methods might fail, or why any sparsification method might fail, is if some nodes just fall off the network. Right, so let's suppose that you live in some rural area, there are only 2 or 3 links to the rest of the world, they all have low weight. Right? Then some of these methods, especially like weight-based sampling or uniform sampling, there's a good chance that none of the edges connecting to the rest of the world are chosen. In which case, well, there's no chance that you'll get infected, and that's not correct. So here we just look at the fraction of nodes that fall off the network. And again, we see that even when we only keep 1% of the edges, this effective resistance does a very good job of keeping almost everybody connected. The other sampling methods lose a couple of percent. So why is that? And I'll bring this in for a landing. Oh, one more thing. Right. So because Alexander was very energetic, I was like, well, again, it's not enough for this thing to work overall. We want to make sure that it works in urban areas and in rural areas, areas with lots of little loops in the network, and areas with more of a tree-like structure in the network. We wouldn't want to present, to Mr. Fauci a method that only works in cities or only works in rural areas. So he said, okay, and he looked up the classification of all these areas of which what they are, according to the government, metropolitan, micropolitan, which means a little city, a small town or a rural, and we found across all of these that the effective resistance did better than the other. So there's a kind of shtick I'm trying to get across here, right? I'm saying, like, if you are working on machine learning, many of your colleagues, not here of course, but in other places that live in darkness, are telling you, oh, just measure the accuracy. Report the accuracy, and if your method is 93% accurate, and last year's method was 91% accurate, you win and we'll get a publication. That's terrible. I mean, yes, it would be great if averaged across all of the inputs you're giving to your algorithm, it gets 91% of them right. But don't you want to know which 9% is getting wrong? Isn't it important to figure out which 9% is getting wrong? Maybe those are the people who belong to a certain minority group. Maybe those are the rural districts or whatever. You want to do, apparently people call this error analysis when you take the time to think about it. I don't know if I was disappointed to realize it needs a name, but you need to figure out where your algorithm succeeds and where it fails. Don't just report that on average it succeeds X% of the time. Okay? Remember that. Good. So why does this work so well? I sort of said this before, so I'll go through this quickly. I mean, it's somehow a good compromise between the topology of the network and the weights. So again, even a low weight edge is considered important if many paths go through it, or if it stretches from one part of the network to another, which is good. In an area where the network is very densely connected and there are lots of ways to get from one place to another, then we think about all those alternate paths. But again, even if you live out here in Montana, if there's only one edge connecting you to the rest of the world, this method considers that edge very important. even if only 3 people travel on it per week. Okay. So that seems helpful.
I guess all of you sort of follow from that idea that if you're computing or if you're sampling a spanning tree randomly with the probability from about a
Right. Right. In fact, an alternate method is to sample multiple spanning trees and then take their union. And that also works pretty well. So, yeah. Okay. So, because you're all potential theorists, and some of you are actual theorists, you might want to know how to prove this. Well, and I am going to stop very soon. So, it turns out that if you preserve that Laplacian in that way that I described before, you can think about a vector which is positive in one part of the graph and negative in the other part of the graph, and then that combination of the vector with the Laplacian tells you the total weight of all the edges that cross from one to the other. So, because it preserves the Laplacian, it is a theorem, a simple theorem, that if you look at any 2 large subsets of the graph, it does preserve the total weight of the edges from one to the other. And that's good because, in particular, if these are the infected folks and those are the susceptible folks, it will preserve the total rate at which new people will get infected. But it seems much harder to prove that it will preserve the probability that individual nodes get infected and also preserve the distribution of times at which they can get infected. I don't think this problem is super hard. I think it's entirely possible that one of you could solve the problem. I haven't solved it. I think it would be fun to solve. So we'd like to prove that Spielman and Srivastava's method works for the SIR model, basically. Okay, so open questions. There are a couple things that might have crossed your mind. One is, wait, so you're saying that you choose a random edge, and then you choose another one, and then you choose another one, and when you do this, you don't even pay attention to the edges you've chosen so far? That seems a little kooky. If you've already chosen some edges that do a good job of representing one part of the network, maybe you're cool with that part of the network and you should focus your attention elsewhere. Well, you may be right, and that would be like an adaptive algorithm, or a bit of a greedy algorithm that at each step adds an edge which in a sense brings you closest to the original graph. And you can do those things, and those are alternate algorithms, and we haven't tried them. What about other things we might want to preserve on a network? So people in network theory and in physics are interested in all kinds of nonlinear dynamical systems on networks, like networks of oscillators that are coupled with each other. That's also related to models of the power grid, where the oscillators are generators. There's this thing called the Ising model, which is a model of magnetic materials, where each node there's a little atom which can point up or down, and it is interacting with its neighbors. So if I gave you a bunch of atoms with very dense connections, could you produce for me a subset of those connections which would somehow preserve the physics of that magnet? That's an interesting question. Another thing is, here I said, okay, I have to finish up Washington. What if you have a cheap method of finding edges in a network and an expensive method which is more accurate? So your geneticist friend gives you this huge correlation network, and it looks like everything is connected to everything else. You want to figure out which edges are really real. Okay? Does sparsification help with that? I mean, is this a reasonable stab at what the biological ground truth is, for instance, in the brain or in genomics? And finally, what about methods where we don't keep all the nodes, but we clump nodes together into supernodes? That's a thing we do in epidemiology all the time. We say, well, everyone in this town, they interact with each other so much, they might as well be one large person where a certain fraction is infected. What are some good, principled, mathematical ways to figure out when you can clump nodes together? And thank you very much. And I hope that this book has been inflicted on you. If it hasn't, then it's not too late.
So I have a few people might come to the class, but we have a few questions. Get a few questions, and great.
2 questions.
Yes.
First, you have some theoretical results showing for linear systems you should have good approximation.
Yes.
And you have experimental results for the SIR. So shouldn't you now construct a dynamical system where, by construction, it should actually fail to preserve the dynamics of the system when you sparsify to understand what's going on?
That's a good idea. Right. But we haven't done that. I mean, the thing about the SIR model is that there are ways in which it's almost linear. Right? So, for instance, when people do approximations of it, they often say, well, everyone has a certain probability of being infected. And if those probabilities are all small, kind of it's the early stages of the epidemic, then to first order everything is linear. It's, it can be linearized, but that doesn't seem to apply to late stages of the epidemic. But you raise a good question. So I mean, it would be good to find something where this method really doesn't work. I assume it would be something where higher order terms are somehow really important, but yeah, it's a good question.
I mean, if it worked as linearized, you could re-linearize it as you go down. I don't know if that's worth. Second question, where were you going with those bats?
With the bats?
Yes.
I was just kind of giving the backstory of why Alexander was interested in sparsifying networks. Sorry. Because his previous undergraduate internship with somebody else was about epidemic simulation of bat disease. Yes?
It's kind of a follow-up for Professor Darker's question. So SIR are typically analyzed quite well with ODAs, but have you explored using PDs to cover more variables like spatial and temporal aspects?
Let me see if I heard the question. That yes, you can approximate the SIR model with systems of ordinary differential equations, kind of like what we were saying before, that we imagine that everybody has a real valued probability of being infected, and then that changes the probability of their neighbors. That is only an approximation. So because of correlations and so on, that in fact, it doesn't give the correct picture of the epidemic threshold, except in some special cases and so on. So we were really interested in discrete stochastic processes, which in some sense is to the extent the SIR model is real, it's like the real model, as opposed to an approximation of it. But your idea about PDEs, where you have like some kind of continuous probability of infection varying across space, and I mean, I guess then you have a manifold instead of a network.
Yeah.
And then maybe you want to sparsify a manifold. I don't know.
Could be by analogy, kind of like the way you draw an analogy with diffusion and mitigation doing it. Right.
Yeah. I don't know. I mean, I wanted to talk about something which really is in progress so that I could get some of you excited. So, I mean, I've definitely not done everything possible here, and neither have my friends. Yes?
So the question is, in this particular network, you went down from 26 million to 1.8 million. Right? So is there a free parameter here? Are you choosing the epsilon, or are you choosing the number of edges, or I mean, for the new network, let's say it's a small network, small derived network, right? So how would I choose the sample size?
I mean, I actually don't know how to go backwards because the display, anyway. So, I mean, the parameter here of these sampling methods is just how many times do you sample, right? So, I mean, the theoretical results say, some constant times n log n, but of course those are asymptotic results. And so for a finite graph, it's not quite clear what we mean. So we literally just tried taking enough samples until we're including 1% of all the original edges, 2% of all the original edges, and at what point does this seem to do a good job? And we were pleased to find that even 5, 6, or 7% wasn't enough.
But that's for this particular network.
That's only for, I mean, you know, I only showed you one graph, right? We did a bunch of experiments, but I only showed you one graph. Now, you know, but there's a reason why we didn't want to do like random graphs, because random graphs are kind of boring structurally. I mean, I love random graphs. I love proving things about random graphs. But we wanted something which was very homogeneous with these different clumps of population and so on. So it would be instructive to do experiments on more real-world networks like that. And Alexander has done some of that as well. One more.
One last question.
So, I mean, a lot of the methods you showed here were based on, you know, some sort of like mathematical, you know, sort of rigorous approach, I guess. Do you know if there's been any research done looking into using like a graph neural network as a sparsifier?
I have not tried Googling that four-word phrase. I think there's a good chance that that someone has. You know, the only, I guess, graph neural networks are at some level local, right, depending on how big their kernel is. And so they're not going to know about sort of long paths from here to there that are outside that kernel, at least as I understand them. But like if a lot of the alternate paths are nearby, like they're triangles and other short loops, then maybe that's a good approach. I mean, specifically, maybe a graph neural network would do a good job of estimating this method, but maybe you can do something else as well. But it's true that stylistically, and I think this is because I mean, you know, I spend most of my day as a theorist, right? I mean, I find, it's sort of religious faith on my part, I find that if you use a really clean, well-motivated mathematical method, where often there's a theorem about its performance in something a little bit different from the real world, like there's a theorem about its performance on random graphs. And of course, no real-world graph is random. Where there's a theorem about its performance for linear things, like Spillo-Srivastava, but we're trying it on a nonlinear thing. It often works pretty well, right, in that more realistic setting. So I guess stylistically, the thing about graph neural networks, if it works, that's great, but will I know why it worked? And will I have a clear sense of when it will work and when it won't? As a scientist, I find it unsatisfying if I don't.
Yeah, it's scary because you lose interpretability.
Exactly.
Well, that's